So let's take a look here. And so we're going to look at this file, but let me then introduce some sections here. The kinematic model. The kinematic model will be a minimal requirement to model a robot. It'll describe links and joints in general. Links and joints. Yeah. For example, in this diagram, you have one link here, and then you have a joint that connects them. Right? If you haven't taken a manipulation class, it's just like you have your upper arm, your lower arm, but your elbow is a link. Right? And so it helps you to know how this can move. Yeah. The shoulder is a little bit different. In the shoulder, we have three joints. Yeah, we have this. We can think of the torso as a link, then the upper arm, but then we can go up and down, and then we can go left and right, and then we can even rotate like this. Yeah, so there's three joints here, all together. So it's a really special. We call it a spherical joint, the very special joint we have on the shoulder. In this example, we're going to have two links and one joint. And it describes an open chain. An open chain is something that has a beginning and an end. Yeah? Different from a closed chain. A closed chain might have this, then another joint here, another link here, another joint here, and another link here. For example, this is an open chain, this arm. This is an open chain, but when I put my hands together, I create a closed chain. And now my motion is different, right? It can do this, but it cannot do this, right? So that's a closed chain. In the URDF, we have a limitation to open chains. It won't work with closed chains. Links and joints are the minimal requirements for the robot definition. And then let's focus on the links, okay? Now each link can only have one parent link. So what does that mean? This is the child. This can only have one parent link. Okay? I need to think about this. We can model like a humanoid robot here. And say, for example, the legs, you have the right leg, the left leg, both of them connect here. But maybe these are treated as separate things. In general, each link has one parent link, and it has one rigid reference frame. So first we say we have a reference frame here. One reference frame. For this link, it's here. For this link, it's here. We say that it's rigid because, let's say that the reference frame is here. When the arm rotates, this link doesn't move. It stays here. Yeah? It doesn't fly somewhere else. So it's rigid. Now, pay attention. The link frame may or not be located within the physical link body. Sometimes this reference frame could be here, even though the link is here. Sometimes. It depends on how you want to describe the system. This often happens if we compute forward kinematics using Dennevit-Hardenberg parameters, the H parameters, okay? Because we have some rules about how to put things together. For child frames like this one, the reference frame is usually going to be, not usually, it's always going to be the reference frame of the joint. Yeah? For child links, you look at the joint, and whatever the reference frame is there, that's the reference frame of this child. This is the base link. That's not just the parent, but the base for the first link anywhere. The reference frame is going to be defined by the CAD system, by the computer-aided design system. You guys often use SolidWorks. When you create the base link in SolidWorks, you have to say, where is this frame of reference going to be? And you can put it anywhere. Yeah, you gotta find one that makes sense to you. The joint frame will belong both to the child link, but also to the joint of the system, right? The joint is going to help the links rotate. This joint has a frame of reference here, but it also has an axis of rotation. And we'll see how we define that as well. Right now, for example, you can think this is the y-axis, so it means this link could go rotate this way. If this link was pointing in this direction, then it would mean that the link can do something like this. So you also have a joint axis that determines the style of the rotation. Like with this elbow, we can do this, but we cannot move like this, right? I would have to rotate my arm to be able to do that. So the joint axis defines, it's the kinematic model, it defines how the robot can move. When you look at Ross URDF tutorials, they're normally going to use 9 fixed parameters and 1 joint variable to describe things. They don't use a DH parameter representation that is commonly taught in classes. If we use DH parameter representation, if you remember from the class, we end up just using 3 fixed parameters and 1 joint variable. Okay, just something to keep in mind. This video is a video for DH parameters. Some of you have seen it before, others have not. It's just as an example to show you what DH parameters are. We're not going to study that right now, okay? Now let's go back to this kinematic model. Let me see, here we go. So let's notice that, for example, we create, this is a comment. Comments in XML always start with exclamation mark dash dash and finish with dash dash. If you don't have that, it's not a comment. So we're going to say, let's create this a base link. You just know that. And so you say, I have a link, and the name is link 1. And then we have the distal link, the one that's further away, we're going to call it link 2. Then we're going to create the joint axis and the joint frame. This element will have the name joint 1. And here in type, you can have fixed or continuous. Continuous means you can rotate. Fixed means you cannot rotate. Okay? And here you establish who is the parent and who is the child. The next 2 things that you need to do for the joint frame is establish the axes and establish, the origin of the frame and the direction of the axes. So if I go back to this diagram and you look at this value, origin 001, right? So you come here and you say, this is the x-axis over here, or let's say this is the x-axis and the y-axis and the z-axis. So if I say, let's put the frame at 001, it means for the joint. Let's not move anywhere in the x direction. Let's not move anywhere in the y direction. Let's move up 1 meter in the z direction. So you move up, and that frame will be parallel to this base frame, will be parallel, and we put it here. Then we look at the rotation. Do I need to rotate by the x, or by the y, or by the z? In this example, we have no rotation. So we have roll, pitch, yaw, x, y, z, 0, 0, 0. So we just translate the frame up by 1 meter. And then we say, but we want the axis of rotation, x, y, z, to point in the y direction. 0, 1, 0. It means, look at this blue cylinder, right? This blue cylinder has its axis of rotation pointing in, let's say this is the y direction. Yeah, which means that the child link can rotate like this. Yeah, if the y direction is in this direction. If the x direction was pointing in this direction, that blue cylinder would be rotated like this. The x direction is coming out this way. And then this child link would rotate like this. Yeah? Does that make sense? So this is a kinematic model, and this file that we see here is the minimal description. Two links, 1 joint. Yeah? We have a reference frame for link 1. If we don't establish by the CAD system, and that's going to be our 0, 0, 0, then link 2 has a frame. That frame of reference is defined by the joint frame. which is shifted from the base by a translation, 001. And then the joint axis is pointing along the world's y direction. Okay? So there's a command called check URDF that can quickly let us see what the file looks like. So for example, here, let me go back to that. What happened here? So we can say Rust CD minimal description, minimal robot description, and then we can say check URDF, and we put the name of the file, which for us is what? Minimal robot description .URDF. Yeah, and so what you get here is robot name is. Oh, I'm using the wrong file. Links and joints. Robot name is one degree of freedom robot. And then it says I can parse the XML. It means I can go through it. It makes sense to me. It says the root link is link 1. It has one child. And the name of the first child is link 2. Yeah, so it's a tool that just helps you understand the URDF. Okay, let's look at the visual model. So we have a new file, one link description.urdf, and this one has the one link description. This one has a little bit more stuff in it. It's the same file as before, but we're adding a little bit to it. Now we're going to add another link. We're going to call it world. World, okay? So we have that link. And then we quickly introduce another joint. And here the name is glue robot to world, type fixed. This means is we're going to create a link that is the reference frame for the world. It will never move. It will be 000. And we want to put the robot link 1, the parent, connected to that world frame. It's going to be fixed, so there can be no motion between them. Yeah? So we say that. And so we say the parent link is world, and the child link is link 1. So we do that part. Now we come to the base link, and we have to give it a name. So we say link name equals link 1. Then we have the visual field. In the visual field, we have two things. We also need a frame of reference, and then we need a geometry for the way that that thing is going to look. Right now we don't have colors yet. But we say, hey, so what I want to create now is a box, 0.2 by 1. Yeah, but how do you put that box in with respect to the frame of reference? Because when you create that box, something like this, the frame of reference is going to be in the middle. Oh, actually, it's going to be placed, in this case, it's going to be in the middle because we created it inside this URDF file. It was not created by SolidWorks. Okay, so we also have the world link here. Yeah, that's going to be 000. Okay, so if this frame origin is 000, we're going to take this frame of reference and put it exactly here. Yeah? And so the box kind of would be like this. Yeah? it would be in the middle. So some part of it will be below 0, some part of it will be above 0. When we move the visual frame 0.5 centimeters up, it's half the distance of this height. This is maybe like length, width, height, something like that. So when we do that, we take this frame of reference and move it up by 0.5. So now the box kind of will be like this. Let me go over here. So now, that box kind of like would be right at the 0 of the floor. The bottom of the box will be at 0. Here, the bottom of the box is at minus 0.5. Here, the bottom of the box is at 0. This is at 1. Yeah? And then the middle of this is at 0.5. So we just shift the box up in the visual frame. Okay, the way that the box looks. Right now, we're not going to visualize the model yet. We're going to keep adding a few more things, and at the end, we'll start visualizing what these things look like. Okay, I'm not going to go through this slide because I've just been explaining it. Yeah, but it basically says the same thing. Now let's look at the dynamic model. This is the first one we looked earlier. So let's look at that again. Joints and limits. Links and joints. Is it this one? No, not this one. Which one is it? This one? No. Sorry, which one was the one that did? What was the first one that we did? I'm making a mistake here. Links and joints that had all the inertia parameters. We have links and joints, online description. Not this one. Not this one. Minimize this mass. One link. Guys, do anyone remember? We just looked at it. This one has that, and maybe it's this one. But earlier we looked at another one like that. Okay, let's look at this one. It's one link with mass. One link with mass. Here we have the visual stuff as before. Yeah, this is our visual frame moved up. Here we have the box size. And then for this link named link 1, we have this inertial section. Okay? Just like the visual field, we also have a frame. We put it in the same place as the visual frame here. We give a mass in terms of kilograms, 1 kilogram, and then we have this inertia. Let's look at what these values mean. Okay. So this is a little bit about physics, but we care about the density, right? We care about the density. Is the density or the mass distributed equally across the object, yes or no? Is one side heavier, or is everything about the same? Yeah? So if if we have uniform density, then the center of mass is in the middle. Actually, this should not go here. Actually, this is wrong. Let me see. Oh, this is with respect to link 1, it's 0 in the x, 0 in the x, 0 in the y, and 0.5 in the z direction. That's where the center of mass is. We're just saying it's going to be in the middle of the box. And this is with respect to, WRT means with respect to link 1, right? Link 1 is the blue one, yeah? And so it's going up by 0.5 in the z direction. Now, we have something called rotational inertia, yeah? The rotational inertia describes the distribution of weight for an object. Now, you need to study this personally if you don't remember. I include 3 or 4 videos on the next slide that give you examples of rotational inertia. It discusses how mass is distributed in the object. Yeah? If we're looking at a 3-dimensional object, we're doing an integral over the volume of the density, and then we have this matrix that changes depending on the shape of the object. If you have a square, a rectangle, a cylinder, a wheel, then you have these kinds of different equations that help us to get an idea of the distribution of weight. Okay? For example, this microphone, the weight is not distributed evenly, right? Yeah, like this falls down like this, which means this side is heavier than this side, right? Things like that. This battery, maybe this rectangle might be distributed evenly. Maybe yes, maybe not. Right? Things like that. So now this we call this the tensor matrix, inertia tensor matrix. It's a 3 by 3. Now if you notice, this is a symmetrical matrix. These two are the same. These two are the same. Let me see. YX, YZ, 60. I think this should be the same. Let me check. This is a symmetric matrix. Normally you have these 9 values, but as long as you have the upper triangle, this triangle here, it's enough to fulfill everything else because of the symmetry of the matrix. I need to check this detail here. It looks different. Yeah, but if it's a symmetric matrix, you don't need all the values because you can fill the other side of the triangle. Yeah. So this is the density of the material. This is wrong. We want to integrate over the volume. This matrix I, not this one, is always symmetric. The resulting rotational inertia, not this one, is symmetric. And then we only need 6 values. We don't need all the values that come over here, the 9 values. This is simple to compute for common shapes. There's many tables that say, hey, this is how you do it. And then CAD programs like SolidWorks will compute this matrix automatically, right? Because the question is, how do I compute these values? SolidWorks will do this automatically internally. Okay? So these are some videos that show you examples of rotational inertia. Yeah, this is a very famous professor in MIT that teaches physics. He's retired, so that's a 40-minute class if you want to take a look at it about rotational inertia. Now, the values of our rotational inertia I will change if the frame of reference changes. Okay? So that matters. And so the question is, where is the inertial frame referred to in the URDF? It's always coincident with the center of mass. Okay? That frame of reference is going to be at the center of mass of the object. Center of mass. URDF can be a little bit complicated for things like this. Some of you are, I'm getting lost. Yeah, because there's a lot of things to take care of. So, and when the robot becomes very big and complicated, there's a lot of things to consider. So you just got to be very careful. SolidWorks CAD systems will help you a lot to take care of a lot of details. And then we'll learn something about Cyclo that helps to make these things more manageable and put them together. And then this also inertial frame of reference is convenient to align it with some axes. And here, the axis is parallel to the link frame. So all what we're saying is, here's the link frame. Here's the object. We have an inertial frame. We're going to put it at the center of mass, and it's going to be parallel to the link frame. Yeah, it's going to be parallel to the link frame. So at the end, this is the world, and then we have this point. That's the link frame for the inertial property. It's at the center of mass, and it's parallel to the link frame. Okay, it's parallel. So that's going to be convenient because the transformation is just very easy. Yeah, so we do that. Finally, you need to try your best to approximate the values, even if you don't know them. Yeah, if you can't get them from SolidWorks, you need to try your best to approximate them. Do not use 0 for the mass. Do not use 0 for the diagonal of the rotation of inertial matrix. If you do that, then the physics engine would end up getting values that are infinity or 0, and you'll probably get a crash in the system. Yeah. So here we have 1 kilogram, and then we make diagonal elements equal to 1. That's not realistic. Normally these numbers will be smaller, but it's okay for the demonstration. So now, even though it's boring, we have enough information to load into a simulator. Yep. So this file that we have here is very boring, but this would be enough to put into Gazebo. Okay. Now, before we visualize it, let's put a movable link on top. Let's have 2 links. Okay. So we now move to minimal robot description without collision. Same as before, we have the world and the link. Okay, base link, okay, has this name. Here's the axes, here's the geometry. Then we have the inertial axes, the mass, the rotation of inertia matrix. You can see how this is described. We have 1, 2, 3, 4, 5, 6 numbers. This is the diagonal parameters, IXX, IYY, IZZ, those are 1. And these are the off diagonals, IXY, IXZ, and IYZ. Yeah, we just take the upper triangle, IXX, IXY, IXZ, and then IYY, IYZ, and IZZ. Yeah. Then here's link 2. Its visual axes will be at the same 0, 0, 0.5. Why 0.5? Not just to be the same as before, but here instead of having a box, we're going to have a cylinder. Yeah. Oh, something to note. Well, let me see. 1 second. Geometry is a cylinder of length 1 and radius 0.1. But you should be asking, in which direction is the cylinder pointing? In the x direction, and the y direction, and the z direction. Well, this is link 2, and that depends on the joint axis, right? Which we'll see in a second. But this link 2 also has inertial properties. We set the inertial link here, mass of 1, and these values 0.1, 0.1, 0.005. Most of the time, if I remember correctly, these values will have more or less this magnitude. 0.005.
I wonder, in reality, how we define those values.
You need to understand the material, the density, and then you do the integrals. You follow the equation that I showed you before. Go back and look at the lecture, and you'll be familiar with that. But it's not the right time for me to explain all of that. But I gave you the reference, so you can look at it. Here's the joints. So joint 1, continuous, link 1, link 2. We're going to move this 1 meter above. Remember that if we look at the base link, how big is that? That is 1, right? So we want to put the joint axes on top of that. And no rotation. And then this is going to be 0, 1, 0, so it's pointing in the y direction, the joint axes. Then we put link 2 on top of that. And this cylinder, let's see. The axis of rotation of the cylinder. I'm not sure. Let's take a look here. How about how this looks? Oh, here's. Let me just add this. A few notes. Set the inertial frame at the center of mass. Mass 1 kilogram. Then these are the parameters. Because this is a cylinder, we can use these equations in the matrix that we looked at before. Ixx and Iyy can be 1/12 mass times the length squared. Izz can be 1/2 mass times the radius squared. So those numbers that we're getting here, if you use mass equal to 1, length equal to 1, radius equal to 0.1, these are the values you're going to get, right? So 1 times 1 squared is 1 divided by 12, 0.08. Here it just rounded off. And then you have 1 times 0.1 squared, 0.001 divided by 0.01 divided by 2, 0.005. Okay, so these equations are kind of, and assuming we have uniform density, then you get these numbers over here. The joint frame, which is also the frame of link 2, it's at the top of the rectangle and it's parallel to the xy plane. Rotation axis set to the y-axis. Here, for inertial parameters, we could add friction properties using Coulomb friction or viscous friction. You can study those differences later. And we could also introduce joint limits, like my arm can only go from here to here, but not further than that. Those are joint limits. Torque limits means how much torque can the actuator apply. Like I can push this hard, but I cannot push harder than that. So I have a torque limit. How strong is my motor? You can also apply that. We're going to visualize in a second. Collision model. A few notes about collision. The robot motion, the way that the arm moves, or the way that the mobile robot moves, depends on also the forces and moments exerted on the robot. Let's say I want to move forward 1 meter per second, but if someone hits me, I'm going to do this, right? My motion depends on external forces as well, gravity, and collisions. When we say dynamics engine, it can also be physics engine, and forces, kinematic constraints. How link 2 moves with respect to link 1, right? Like they're connected, they're not going to get disconnected. Yeah, you're controlling that. It enforces angular accelerations. For example, if I do this very fast with this joint, my arm will tend to want to keep moving in this direction, right? This has an effect on on link 1 to do this a little bit. Yeah, if I do this a little bit, it's like and I don't stop it, everything begins to bounce, right? Because there's forces created by this one that influence this one. Yeah, so those things are considered by the dynamics engines. Angular acceleration caused by gravity, joint torques exerted by actuators. Joint torque simply means the force, the rotational force of the motor, of the actuator, and collisions. So to include the influence of contact forces, we must enforce a collision model. Okay, and so let's open this one, minimal robot description. So we have the same thing, base link, inertial, visual. Oh, let me see, did I skip that? Collision. Okay, so you have this part here. This is new, but this is our collision model. Just like visual, just like inertia, you also need a frame. We put it in the same place as everything else. 0, 0, 0.5. Now, the collision model needs a geometry. This is like specific to the collision model. Okay, we have two links. Those two links will also have a geometry. Right now, we have very simple shapes. We have a rectangle, a box, and we have a cylinder, right? But if you think about Baxter or UR5 or Atlas humanoid robot, those links may have very complicated shapes, right? In the collision model, you can say, let me have a shape that is as complicated as the original one, or let me have something more simple, okay? In this case, we're going to have the same thing, box. So it's the same shape, we have the same parameters. This one, we're making it a little bit smaller. I'll explain to you why in a second. So we have the same origin, we have the same geometry, and we almost have the same size, okay? For the cylinder, it's going to be exactly the same. We go down here to the child link. We have collision. Here's the origin, same as before, and here's our cylinder, length 1, radius 0.1. Exactly the same, okay? Now let me explain a few things that I've mentioned here. When do collisions occur? Collisions occur when solids intersect. So you have maybe a box here and a cylinder here. Imagine that your arm could keep going, keep going, keep going, and then they would touch here, right? There would be some kind of intersection. Intersection. When there's an intersection, they collide. Let's say you have a cylinder here and a cylinder here. If you do this, boom, they touch, they intersect. Then there's a collision. When they intersect, they create interaction forces and torques. At the point of contact here, you may only have one point of contact, but maybe you have multiple points of contact with more complicated shapes. Yeah? Now, something you need to know is that collision checking can be a computationally expensive process. Very expensive. Because actually, the system needs to check collisions between all the links of the robot. Between this and this, 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 this and this and everything. Yeah? In general, I mean, there's better ways or smarter ways or more advanced ways to do things, but basically you're checking intersection between everything and everything. It's computationally expensive. So everyone is always trying to find how to make this a less computationally expensive process. So let's say you have a really nice advanced model for one of your links. Yeah? Instead, you might choose a very simple collision model. Yeah? For example, so if the visual model is a complex mesh, just choose a simple primitive that surrounds the mesh. A mesh is created in a program like SolidWorks. It's a surface of triangles. Let's say you have some kind of surface like this. And in here, how can I do this? You might have a lot of triangles. And these triangles might be made of subtriangles. Many of them. Yeah? And those triangles help you to create very smooth surfaces. You might have 10,000 of them to create a very smooth surface. That's called a mesh. So let's say that you have something like this, right? To simplify it in your collision model, you just say, let me approximate that mesh with a primitive object. Let me draw a cylinder around it. Yeah? It's a little bit bigger than the mesh, or it could be a little bit smaller, normally a little bit bigger, and it's not exactly the same, but it's enough that, maybe you say there's a collision when you're here instead of here. But it simplifies the computation a lot. Instead of having 10,000 points, maybe you have 2 parameters that describe the surface. Yeah? So if that's what we do, if we have a complex mesh. Now you can still choose, if you have a really powerful computer, maybe say, I don't care, let me keep the mesh for the collision model. Okay? If you have a simple visual model, then the collision model normally is going to be identical. There's one more thing that you need to be aware of, is that you need clearance between the links. Because if you have like a cylinder here and a cylinder here, they might be touching at the joint. So this might say, oh, they're always colliding. So you need a little bit of space here, especially when you rotate, so that they never touch. So that they never touch here. So this effort here to make this length a little bit smaller is to say, oh, let's move that back 3 millimeters. Yeah, or 30 centimeters, sorry, 30 centimeters, so that they never touch. Okay? Does that make sense? That's called clearance, joint clearance.